So the quiz, I think it's open for 4 or 5. Once you start it, you have 4 or 5 minutes to finish it, and it will close entirely at 9:10. So if you haven't done it already, head over to D2L. Under quizzes, there should be something called Video 1.3 Startup available, and so you should take that. And then once it's 9:10, we'll get into material. And this is going to be the case whenever we have whenever we end one lecture at the end of a video and we start a new video in the beginning of the next lecture, which isn't always going to happen. Sometimes we're going to stop in the middle of a video. But if we're ever starting a new video at the beginning of class, I'm going to open up the startup quiz 5 minutes before class, so you can take it ahead of time if you want, and it'll be open until 5 minutes after class. All right, 12 of you have taken this. And let's see, there's 22 of you here, and then 2 more in class. Total of 24 out of 33 students, which isn't great for the second week. Yeah, that's frustrating, James. Do you go by James? All right. Let's see. I feel like there was something else I was supposed to set up before class. Oh, well, if there was, I'm sure I'll figure it out eventually. All right, about 2.5 more minutes, and then we'll start talking about stuff. Yeah, so I'll upload the question for those of you in person. The question that was just asked was, will I upload the video question answers, corresponding to the video questions in D2L? Will I upload the answers after class? The answer is yes. Those will appear on D2L after we the solutions to the pencil and paper problems will appear on D2L after we go over the material in class, because that way I want the point of having you attempt the problems before class is that I want you to actually attempt them. I don't want you to just read solutions. So I'll post the solutions afterward. All right, so about a minute and a half more, and then we will get on with material. So let's see. 24 of you have taken this, so that's almost everybody here. So if you haven't finished the startup quiz yet, you should do that in the next minute, because then we're going to move on. And again, this is how on any class that we're going to start a new section at the beginning of class, this is how it's going to go. We'll spend the first 5 minutes of class time on the startup quiz. Sometimes we'll pick up a new video, a new section in the middle of class. And in those cases, I will pause for 5 minutes to have you take the startup quiz during class. That'll happen sometimes. But if we're ever starting a new video at the beginning of class, you'll have the startup quiz at the very beginning. So the first 5 minutes will be dedicated to that. And then throughout class, you might have questions corresponding to examples that we work on. on Fridays, we'll have end of the week quizzes, as I told you about. Yeah. All right. It is officially 9:10. So let's start up some material. So, okay, I lied a little bit. We're not going to start video 1.3 right away. I just wanted to get the startup quiz out of the way. We're going to go back. We're going to backtrack a little bit. I'm very sorry to have deceived you. So if you recall, on Friday, we finished the class on this problem, where I asked you to write down. Together we wrote down the sample space of this problem where you're observing an intersection where there's 3 possible choices for cars to turn: left, right, or straight. I guess straight isn't really turning, but there's 3 directions for a car to go. So left, right, or straight. Yes, I can share the screen. Maybe that's the thing I was trying to think of that I hadn't done. Sorry about that. Aha. All right. Thanks for that, for pointing that out. So we did this example, right? Every car can either go straight, right, or left. We wanted to write down the set of all possible outcomes for watching 3 cars in the directions that they go. And the set of all possible outcomes for the directions that those 3 cars go is there's 27 possibilities. The first car could go right, the second car could go right, the third car could go right, the first car could go right, second car could go right, the third car could go left, and so on. I'm not going to read all 27 of those. And then we started asking some kind of sub-questions. So list all the possible ways that all the cars could go the same direction. Well, they could all go right, they could all go left, they could all go straight. List all the ways they could go different directions. So you could have right, left, straight, right, straight, left, right, straight, right, straight, right, left, right. Those are all the different ways that the 3 cars can each go different directions. There's 6 of those. And then I had you answer this one as an in-class question. That one didn't count toward your grade because it was first week stuff. But I had you answer as at the very end of class, and we didn't get to go over it together. The question: list all, or I guess problem, it's not really a question, list all outcomes in the event C such that exactly 2 of the 3 cars turn right. So let's do that. So you've already answered this, so you already have seen the answer, whether you remember it or not. But we could have, so if we need exactly 2 of them to turn right, right? That's what it says. We need exactly 2 of the 3 turn right. So we can't have all 3 of them turn right because that's not exactly 2. So if I instead I had said at least 2 cars turn right, then all 3 turning right would also be included. But that's not going to be included. We need exactly 2. So we could have the first 2. And then the third car necessarily isn't turning right, which leaves 2 options. It could go straight or turn left. So we could have right, right, straight, right, right, left. We could have the first and third cars go right, which leaves 2 options for the middle car. Could go straight or could go left if the first and third cars both go right. Or the second and third cars could both go right. So let's see. We would have straight, right, right, or we would have left, right, right. I'm trying to write too far down on my iPad. Whenever I do that, it screws up. And that's it. Those are all the different ways that exactly 2 of the cars could go right. All right. And then, so are there any questions about this problem? So this, the point of this example is really just getting you comfortable with writing down sets that match descriptions in words. Because so there's, let me say kind of a disclaimer about this course. This course is very much problem-based. It's very much a problem-solving class, more than probably any other math class you've ever taken. Because in calculus, you're just doing derivatives on repeat, or taking integrals on repeat, or finding the convergence of series, or something like this. And of course, there are applications tied in, but really, it's a very cookie-cutter course. It's very much you just learn these differentiation rules, and then you regurgitate them on exams, so on. In this type of course, in probability, most of the problems, maybe not most, but a lot of the problems that we can and will address in this class are going to be what are unfortunately called word problems, which in real life are just called problems, because in real life, no one comes up to you and says, hey, take the derivative of this function that I'm giving you. People say, hey, what time do we have to leave in order to get to a restaurant on time? Of course, that question is only applicable pre-pandemic. But, what time do we have to leave in order to get to class on time? Something like this. It's a word problem. And so in real life, every problem that you've ever solved is a word problem. So you shouldn't be afraid of word problems. I know a lot of students say, oh, I don't like word problems because I have a hard time translating it to math, which is okay. That's the biggest step. You have to take words and you have to transform it into this language of mathematics, and then you can solve it. Because once you have it in sort of this setup as a regular old math problem, it becomes like any other math problem that you ever see. But the trickiest step usually is translating these words into the language of mathematics. And again, as I was saying last week, the language of mathematics that we use, that's sort of at the foundation level of probability, is set theory. Excuse me. And so if we say, for example, we want to find the probability that 2 of these 3 cars that we just observed turn right. This is the kind of question that we could feasibly ask. If we assume that the probability that cars turn left, right, or go straight with the same probability, so any individual car that drives up to an intersection has the same probability of going left, right, or straight, then if we wanted to figure out the probability that exactly 2 of those 3 cars turn right, we would set it up like this. We would write down as a set all the possible ways that exactly 2 cars would go to the right. And we'll talk more about this later, either later today or on Friday. And so being able to take these words from this problem about cars turning in directions, which I understand is kind of a silly example, but it's also illustrative. Being able to take words from this problem and write it down in this language of mathematics, which is currently is set theory, is very, very important. It's how we approach every single problem in this class. So this is just getting you comfortable with doing that, taking these words in the problem and writing down as a set the stuff that we care about. So that's the point of this problem. I have the second problem here, which is kind of the same. It's a very similar problem. I'm going to skip it. I'll put it. So one other thing that I should say is that I'm going to start maintaining a list of practice problems, so you guys don't have any formal homework in this class. But I'm going to maintain a list of practice problems that will eventually serve as a study guide for your exams. So I'll put on D2L, I'll post under content, there'll be a module called practice problems. And I'm just going to start sort of a running list of problems from the textbook and elsewhere that you should be able to do. And I'll also post hints for each one of the problems, so you get an attempt of them. You can attempt each one of these problems, and then if you get stuck, you can't get it, you can reference the hints, and maybe that'll point you in the right direction. I'll also post solutions to all of them. So you'll have sort of this running study guide that you can do and should do. So I'll just put this problem on that study guide, or those practice problems. Okay, any questions about any of the stuff I just said? As usual, if you have any questions, you should, oh shoot, that's not what I meant. Not file, I want to print out. If you have any questions, just type them in the chat, as usual. So let's see, video 1.3. Let's see, I called this one 1.3 lecture marked. That's it, because I drew on it already. All right, but we'll get there. So, all right, and so I think I've already said this out loud, but to repeat it, a lot of the stuff in this class is going to say fall 2020, or the dates might be wrong or something like this. It's because I'm recycling material, because that just makes my life so much easier. So this is obviously spring 2021. All right. So as usual, the first thing we're going to do from this set of notes is we're just going to go over those conceptual problems from the the video questions I asked you, and then we're going to do a couple examples. So we'll just see how much we get through. I have a feeling we're not going to finish this section today, and we'll finish it on Friday, which means that there's a good chance we'll start video 1.4 in the middle of class on Friday. So you can expect to have a startup quiz in the middle of class. So you should make sure that you watch video 1.4 before class on Friday. So all right, let's answer these questions. So this first one is just developing language. So with any subject in mathematics, or really any subject across any field, we need a common language. There's stuff that we're going to refer to often enough that we just want to give them words, so that we don't have to keep describing with a bunch of words the thing that we could describe in a single word. So this is just some vocabulary for you that we're going to use again and again and again. It will become comfortable, I promise. A random experiment. I've already defined this in class, but here we define it formally. It's any process with an uncertain outcome. So there's, you can come up with as many examples as you like, because it turns out most things in life are random experiments. You don't actually know how things are going to end ahead of time, even if it seems really, really certain. Basic examples I'm going to use in a lot of examples in class are things like tossing a coin. So say a fair coin has one side is heads, one side is tails. You don't know which side is going to come up ahead of time. It's a 50-50 shot of getting a heads or a tails. A die roll, say a fair 6-sided die, you don't know what number is going to come face up after you roll it. You can also come up with examples where you don't know the probabilities ahead of time. So with, say, a fair die, the probability of getting any face of that die is 1 in 6, right? Because there are 6 faces, they're all equally likely. So it's a 1 in 6 chance of getting any one of them. There's things that we can't actually with any certainty to predict the probability of, things like the number of goals scored in a soccer game, or say the outcome of a Super Bowl or something like this. These are all examples of random experiments. So a random experiment is the physical process that you're performing. It's the thing that's happening in real life that we want to know something about. So it's tossing the coin. It's not the outcome of the coin toss. The random experiment is the physical act of tossing the coin. Okay, the outcome is the result of the random experiment. So in a lot of cases, the thing that we're going to concern ourselves with is the outcome of a random experiment. We want to know, if we toss a coin, what is the probability that we get a heads? If we toss 3 coins, what's the probability that we get exactly 2 heads? Something like this. So the outcomes you perform this random experiment, and then whatever happens at the end of that random experiment is the outcome. So if the random experiment is the act of tossing a coin 3 times, then maybe heads, heads, tails is your outcome. Something like this. Okay, and then the sample space is, if you've taken discrete math or something like, or another course where you've discussed set theory, you may have called this the universal set. But the sample space in probability, the universal set is called the sample space. It's the set of all possible outcomes of a random experiment. So if you, so it is a set. The sample space is a set, and it's the set of all possible outcomes. So if you are talking about tossing a coin, the sample space would be the set containing heads and tails. So H comma T, what I wrote here. If you roll a fair, well, it doesn't necessarily have to be fair, but if you roll a 6-sided die, then the set of all outcomes would be 1 through 6, 1, 2, 3, 4, 5, and 6. If you want to talk about the number of goals scored in a soccer game, the sample space would be, it would start at 0 because you can't have negative goals scored. You'd have 1, 2, 3, 4, 5. It would actually be unboundedly large. It would be all of the non-negative whole numbers, all the non-negative integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on up through infinity, because theoretically, a soccer game could have as many goals as you like scored. You could be an unboundedly large number of goals scored. It'd be a very, very boring game after a while, but it could theoretically happen. So the sample space of goals in a soccer game would have to include numbers as big as you could possibly imagine, which means it has to go off to infinity. But it's all the whole numbers, because you can't have non-whole numbers of goals scored, for those of you unfamiliar with soccer. So, all right. And again, any questions about anything at any point, please type it in the chat, or if you're in person, you can ask me. All right. What is the sample space of the random experiment defined by tossing a 2-sided coin twice? So this question is really just to get you comfortable with the fact that random experiments don't have to be a single action. It could be sort of an accumulation of several actions. So a random experiment could be tossing a coin twice. It could be tossing a coin, then rolling a die. It could be tossing a coin, then playing a game of soccer. The random experiment is the whole collection of however you define it. It doesn't have to be a single coin toss. Here it's 2 coin tosses, which means that each outcome, any outcome of this random experiment where we toss a coin twice, is an ordered, it can be written as an ordered pair. So each outcome is an ordered pair of the form, the outcome of toss 1, comma, the outcome of toss 2. So if you, on your first toss, you get a heads, and your second toss, you get a tails, the outcome would be H, comma, T. If you get a heads and heads, the outcome would be HH, and so on. And so the set of all possible outcomes, there's 2 possibilities for the first coin toss. There's 2 possibilities for the second coin toss. There should be 4 total, because T times 2 is 4. And so the sample space contains the outcomes heads, heads. You get heads on the first, heads on the second. Heads, tails. Heads on the first, tails on the second. Tails, heads. Tails on the first, heads on the second, or tails, tails. Those are the 4 possible outcomes of tossing a coin twice. If we toss a coin 3 times, we would have 8 different outcomes. I'll leave it to you to write those down. But if we say we tossed a coin and then we roll the die, we'd have 12 possible outcomes where we could get a heads on the first, and then a 1, 2, 3, 4, 5, or 6 on the second. So that's 6 possible outcomes there. Or we would have a tails on the coin toss, and then a 1, 2, 3, 4, 5, or 6 on the die roll. So that's 6 more. That's 12. So the sample space of a random experiment, even if we're repeating, even if it's comprised of multiple physical actions, it still contains all of the possible outcomes where the outcomes might look like ordered pairs. Or if we were performing, say, if we're tossing a coin 3 times, they would look like ordered triplets. So for example, if we tossed heads, heads, tails, our outcome would look like HHT. Okay, that's just the notation we're going to use to denote outcomes of these types of random experiments. Okay, what is an event? All right, this is maybe the first vocabulary word that doesn't necessarily sync up with your intuition of how we would define it. So an event is a collection of outcomes. It's a set of outcomes. So very, very importantly, an event is a set. And this is why in probability theory, we base everything on set theory, because we're going to talk about, when we start talking about probabilities, we're going to start talking about the probabilities of events and nothing else. The only thing we can define probabilities of are events. And events are sets. So really, we're finding probabilities of these special kinds of sets that are called outcomes, or sorry, that are called events, which are full of outcomes. And this is why everything is rooted in set theory. So as an example that I have written here, in the previous problem where we talked about tossing a coin twice, we might want to ask a question about the probability that we get, let's see what I say, at least 1 heads. And if so, then we would be considering the probability of the event that we have heads then heads, because that's certainly at least 1 heads, heads then tails, because that has at least 1 heads, or tails then heads, because that has at least 1 heads. But we would exclude from this event, we would exclude from this set the outcome that doesn't have any heads in it, which is tails, tails. Okay, so if we want to find the event where we get at least 1 heads, we can write it down as this set, A. Okay, so this is again language that you're going to have to become comfortable with. So when we write down events, when we write down the things we want to find the probability of, we're going to write them down as sets, and they're going to look like this. They're going to be sets full of outcomes. Okay, and once we start talking about finding probabilities, it's almost always, not in every case, but in a lot of problems that we do, especially early on, it's going to be very beneficial to be able to write down the sample space, being able to write down all the possible outcomes. Because if you have the sample space in front of you, then writing down any event is just a matter of reading through the sample space and picking out the outcomes that match whatever you care about. So in this case up here, the sample space we're tossing a coin twice is this guy. Heads, 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 tails, tails, heads, tails, tails. And so finding all of the outcomes that contain at least one heads is just a matter of looking at that sample space and pointing at at each one that contains at least one H. So writing down the sample space is super useful if you can. Sometimes the sample space is super large. Sometimes it's infinitely large, like that soccer example I said. And then, of course, we can't write that down because that's infinitely large. We can write it down in some notation, but we can't write down every single outcome. Okay, so let me just remind myself. This is the last conceptual part, right? Yeah. Oh, no, it's not. How many more I got? Okay, it's just these two. All right. Conceptual problem 4. This is, I've said a few things are the foundation of probability, one of which is set theory. These axioms of probability really are the foundation of probability theory. So in mathematics, when we call something an axiom, this means it is a statement that we accept as true without proof. So in mathematics, every statement that we take as true, usually we have to prove. If we can't prove a statement, then we can't assume that it's true. But the foundation of any subject is rooted in what are called axioms. And so the axioms are these, what are typically mutually agreed upon as self-evident statements that we don't have to prove. So essentially, we say, if in probability theory, if these 3 things are true, then we can prove everything else in probability theory that we know of. So these are the 3 axioms of probability. The first one simply says probabilities cannot be negative. Probabilities cannot be negative is the first axiom of probability. This seems reasonable because what's a negative probability? I don't know. That wouldn't make any sense. The probability, so again, I said just a minute ago that the probability, that the things we're going to find the probability of are events, right? We're going to find the probabilities of events, and events are sets. The sample space, the set of all possible outcomes, is an event. So the sample space, S, is an event, which means we can find its probability. Now, the sample space contains every possible outcome of a random experiment. And so if we ask ourselves, what's the probability that after performing a random experiment, we see an outcome? The answer is 1. The probability, so let me backtrack just a tiny step here and say, so that everybody's on the same page, probabilities are defined between 0 and 1. In real life, if you talk about probabilities, if you talk about the chance it's going to rain today or something like this, you'll probably say there's a percentage, 70% chance of rain or something like this. In math, we normalize those probabilities, so we write them between 0 and 1. So a 70% chance would correspond to 0.7 probability. And so 100% chance is a probability of 1. So probabilities live between 0 and 1. And so, okay, if we ask what is the probability of the sample space, what is the probability that we see any possible outcome? The answer has got to be 1, right? Because we perform a random experiment. We say we roll a 6-sided die. The sample space is the set containing the numbers 1, 2, 3, 4, 5, and 6. The probability that we see one of those numbers is guaranteed. And okay, you could be a jerk and you could say something like, "Oh, what if it lands on its side or falls like on a crack or whatever?" Then I don't care about that case. I'm considering the theoretical case where we know for a certainty it's going to land with A face up. It's going to be one of those 6. So the probability of the sample space is 1. The probability that something happens is 1. That's the second axiom of probability. So these both seem reasonable, right? Probabilities can't be negative, because what does that mean? And the probability that something happens when we perform a random experiment is 1. Another way to think about axiom 2 is to say, imagine that something outside of the sample space happens. So we perform a random experiment and we get an outcome that isn't in the sample space. Well, that doesn't make any sense, right? Because the sample space contains all possible outcomes. And so if an outcome occurred that wasn't in our sample space, that just means we missed it. And it is actually in our sample space. Because it's a set of all possible outcomes. And if an outcome occurs, it has to be in the sample space. So, okay, those are the first 2. The third one is really the biggie. The first 2 make a ton of, make all the sense you would ever want them to make. The third one isn't necessarily as intuitive, but it's also probably the most useful in terms of actually finding probabilities. The first two kind of keep us constrained between 0 and 1, probabilities between 0 and 1. The third one is really the foundation. I call a lot of things a foundation so far, but this is really the foundation for how we find probabilities. This gives us sort of our mechanics for actually finding the probabilities of events. And so the third axiom of probability says that if we have a collection of disjoint events, so remember, disjoint means that the intersection of these guys is empty. So these guys don't overlap. So and really, I should have said that these guys are pairwise disjoint. Not just disjoint altogether. So if these guys are pairwise disjoint, meaning that for every I and j, their intersection is empty, so no two of these sets overlap, then the probability of the union of all of these guys is equal to the sum of their probabilities. So, okay, how do we make sense of this? Well, the left-hand side, I'm going to draw a little line here. So P of A1 union A2 union so on union AN. This is the probability. I'm going to abbreviate probability as prob. I hope that's not a problem. Probability that A1 or A2 or A3 or, yeah, not a prob. I kind of expected that to happen. Somebody in the chat said not a prob when I said probability is going to be abbreviated prob, which I'll give it to you. That's not so bad. All right, so it's probability that one of these events occurs. So A1 occurs or A2 occurs. Because remember, the union of two sets you should think of as the OR operator. Because a lot of your computer science majors, you should think about, say, well, I'll write down a little example in just a second. But we're asking what is the probability that at least one of these occurs. So A1 occurs or A2 occurs or A3 occurs and so on. If none of these overlap with each other, so if A1 occurs, then none of the other ones can possibly occur. If A2 occurs, none of the rest of them can possibly occur, and so on, then the probability that we see any one of these, what according to the third axiom of probability, is the sum of the individual probabilities of these events. So here, let's do a little mini example here. And let's say we roll a 6-sided die once. And we want to find the probability that the roll results in a number, let's say, greater than 4 or exactly 1. I don't know why we want to do this. This is just the thing that we're doing because we're bored. Because quarantine takes its toll and we're stuck with just rolling dice. So we want to find the probability that we get a number that's greater than 4 or exactly 1. So let's let A be the event. The roll is greater than 4. Okay, there's maybe a little bit of ambiguity here. Yeah, it could be some sort of convoluted rule for a board game. That seems like the kind of thing that a board game creator might do. And then, oh, cool, I'm getting a spam call. Hold on. I've really got to disconnect my phone from my computer because that's very frustrating. Sorry if there was suddenly a loud ringing in your over Collaborate Ultra. Okay, maybe it doesn't actually. That would make sense that it doesn't actually project the phone ring through my my mic. So that would just be a terrible feature. So okay, so A is going to be the event that the roll is greater than 4. And so when I say greater than, I mean strictly greater than. And if I say greater than or equal to, that's when it's non-strict. So when I say greater than, just assume that means you. After this, I'm probably I will very rarely say in words greater than. It might come up again, but usually I'm going to actually write this out. It's an inequality. I'm going to write the strictly greater than symbol. So we can write A as the set containing 5 and 6. Okay. Now, let B be the event. The roll is a 1. So B I can write as the set containing 1. I'm going to zoom out a little bit. Okay, so I have this one set containing 5 and 6. I have another set containing just the number 1. These are mutually exclusive, right? These are disjoint sets because 1 isn't contained in A, and neither 5 nor 6 is contained in B. So they don't share anything in common. So I'm going to move over a little bit, unfortunately. So the what I just wrote is going to be hidden. So I'm going to hop over here to finish the problem. So A intersect B is the empty set, which means these guys are disjoint. So the condition for the third axiom of probability is satisfied. So we have two sets. We want to find we have two events. We want to find the probability that this die roll lands in one of those two events, either greater than 4 or exactly 1. And so I can apply the third axiom of probability. So I can say, so then by the third axiom, so a question was asked in chat, could it just be A is 1, 5, and 6, or do they have to be separate because the problem said or? The answer is that would work. You could combine them into a single set. But that's sort of dependent on the third axiom. So the only technique we have for finding probabilities at this moment is the third axiom of probability. And so the rule by which we would justify the answer to your question, so the rule that would allow us to combine 1, 5, and 6 into a single set, rather than looking at the set containing 1 and then separately the set containing 5 and 6, is the third axiom. So the third axiom is what allows us to kind of smash those together. But yes, in general, you will be able to combine things in this way. Okay, so by the third axiom, the probability of A or B is equal to, actually, you might not even need the third axiom. I would have to think about it. You might be able to get away with this without the third axiom because if you just took the union A, union B, then you would end up with the set 1, 5, 6. And then you would just be looking at the probability of something new. The way that the third axiom comes in is that the way that we would actually break that down to find the probability to begin with is by sort of decomposing the set 1, 5, 6 into individual sets, the set containing 1, the set containing 5, the set containing 6. And then we could find the probabilities of those individual guys and then add them all together using the third axiom. So this is one of those questions that answering it is like touching on something that we're going to talk about in just a minute. So we're like almost able to answer it, but it's touching on stuff that we haven't strictly covered yet. So the answer might not feel very satisfying at the moment. That's my point. Okay, so by the third axiom, we can break this up into the probability of A plus the probability of B. Okay, and now, so this guy, this is the probability of getting a 5 or 6. And this is the probability of getting a 1. Right? Okay, so let's think about this and just think about this sort of in line with the intuition that you've built up over an entire life of rolling dice, assuming you've rolled dice ever. So really what we're asking here is, so as Jeremy said it in the chat, really what we're asking here is what is the probability that we get a 1, 5, or 6? And so those are half the faces of the die, right? That's 3 out of the 6 faces. So the probability should be 3 over 6, right? And this makes some sense. This, there's nothing really that unintuitive here, because we know if you want to find the probability, if you can either get a 1 or you can get a 5 or a 6. This leaves 3 possible choices out of 6. They're all equally likely. There's a 3 in 6 chance of getting these. So what might actually be a little bit more illustrative for the axiom of probability, the third axiom of probability, is if we write down something that doesn't satisfy the condition. If we write down, say, 2 sets that are not mutually exclusive, and we try to find the probability. So I'm going to hop over here, just to the right of this, and say, example of when axiom 3 does not apply. Okay, so I'm going to write this in fewer words. Instead of writing this all out in words, I'm going to write this down a little bit quicker. I'm going to say let's see, I've used A and B in that first part, so I'm going to write C and D here. Let's see. So here, I'll do this. At least I'll say we roll a die. We once again roll a die. And whenever I say, whenever I don't specify the number of sides of a die, I mean a 6-sided die. If I ever mean anything other than a 6-sided die, I'll specify that. If I want to say a 20-sided die or 10-sided die or whatever, I'll specify that. If I just say a die, I mean a fair 6-sided die. So all the faces are equally likely, and it's 6-sided. Okay, so we roll a die. Let's let C be the possibility that we get an odd number. And actually, we'll just keep B. Okay. So C is the event that we get an odd number on our roll. B is the event that we get a value that's bigger than 4, strictly bigger than 4. So we want to find the probability. We want the probability of B union C. So this is the probability of rolling an odd number or a number bigger than 4. Okay, but the issue here is that if I try to apply the third axiom of probability, then I'm double counting that 5. So this guy contains 5. This guy also contains 5. And so this here double counts the probability of rolling a 5. So this is not equal because, okay, so the probability of getting an odd number would be 1 and 2. It'd be 3 and 6 because 3 of the 6 faces are odd numbers. The probability of getting a 5 or a 6 would be 2 and 6. So you add those together. This would claim that the probability is 5 over 6, which by itself doesn't sound like a problem because that's less than 1. But here, what if we just, I'm not going to write anything down, but just as a thought experiment, let's change this up a little bit. And let's say, instead of writing down B as the event where I get a 5 or a 6, let's rewrite B as the event where I get, say, a 3, 4, 5, or 6. So I'm going to put 4 numbers in set B. Then if I tried to apply this, if I tried to write down the probability of B plus C as the probability that I'm looking for, then I would have 4, 6 plus 3, 6 as probability of B plus probability of C, which would be 7, 6, which is bigger than 1. So that's saying that the probability of this event is bigger than 1, which is nonsense because you can't have probability bigger than 1. So, okay. So this axiom, I spent more time on it than I intended to, but it's important because it's how we're going to going forward find probabilities. It also should become natural as we start using it because it's going to come up a lot. It's going to become a very natural notion as we go forward. And so these two examples are intended to illustrate why it works when it does and why it doesn't work when it doesn't. And so the very, very important part is that you need these sets to be disjoint. You need this. If you don't have this disjointness of your sets, if they're not mutually exclusive, you cannot apply axiom 3 as illustrated in this example over here. Because if they're not mutually exclusive, then when you find these probabilities by adding them together, you're going to double count stuff. You're going to double count probabilities, which is going to overestimate the probability of this happening, which is obviously not what you want. So let's see. We have 4 minutes left. Let me start. Or does anybody have any questions? Any more questions? Okay. So one of these conceptual questions, I asked you to just work through these problems or these statements that he did in the video. And the reason I asked you to do this is because they're important enough. These 6 things are going to come up again and again and again throughout the semester, particularly this first one, which I'm going to give a name to because it's going to come up. So this is going to come up often enough that that I want to just be able to refer to it by a name. And so this I'm going to call the complement rule. So the complement rule, and I'll say what it is out loud in just a second, but the complement rule and what's called the inclusion-exclusion principle are 2 of the most important techniques that we're going to have throughout the entire semester. These are going to come up over and over and over and over and over again. So down below, I've already illustrated parts A, D, and E because these are the 3 that are probably the most important. But let's see. We have 2 minutes left. So I'm just going to read through these. We'll talk through them next time, and then we'll do these examples at the end of the video lecture or the end of these notes. So, but let's just talk through these. So the first one says that the probability of a complement. So remember that superscripted C there means the complement, right? So that means that the A complement is everything that's in our sample space that is not in A. So I've illustrated that down here in this black box. The black rectangle represents the sample space. That blue circle represents A. So what I shaded in green is everything that's outside of A, which is A complement. And so if the sample space has probability 1, then if I were to cut out the probability of A from that sample space, I would be left only with the probability of A complement. So let's see. I'm not going to get through all these this time. So let me leave you on one thing, on one important way to visualize probabilities. You can visualize probabilities as relative area. So look at this thing I drew here. that black rectangle represents the sample space, right? The area of that sample space represents its probability. So the area of that sample space I'm saying is 1 because the sample space is probability 1. So in my picture, I'm going to draw it with area 1. Then the relative area of any set I draw within S, any event I draw within S, is the probability of that event. So the area of that blue circle A is the probability of A, which means that the area outside of A that's still in S is 1 minus the area of A, right? Because I'm just cutting out that area, cutting out the area of A, which means, but by the same analogy, by equating area with probability, the green shaded area